So, I will continue discussion on the polarization of double refraction. So, we have seen these two types of uniaxial crystal, calcite crystal and quartz crystal. So, double refraction is basically occurs because when light enter into this crystal, so it split into two rays. So, one is called the E ray and another is called the O ray. E ray is pi polarized and O ray is sigma polarized. So, one thing is clear that basically when unpolarized light is falling on the entering into this crystal, unpolarized light is nothing but the we can consider mutually perpendicular two electric component. So, basically these two electric components they become separated. So, O ray and E ray all the time it is polarized light. It has only one direction, linear direction polarization, okay. Electric field vector is in a particular direction. So, depending on the direction of the electric component, so it becomes sigma polarized or it become pi polarized. So, sigma polarized one is called the O ray, ordinary ray, and pi polarized one is called the E ray. So, in uniaxial crystal, velocity of E ray and O ray or refractive index of E ray and O ray are same along a particular direction, that is called the optics axis. So, uniaxial crystal, so it has a one direction, it is called optics axis. So, in that direction the O ray and E ray their velocity or refractive index of the metal with respect to this O ray and E ray are same. In other two direction, if that direction we take as a one of the principal axis, so that is z axis. So, other two direction x axis and y axis, these two directions are basically isotropic. In that sense, you can tell isotropic means same refractive index and velocity are same along the x axis and y axis, but it is same for a particular ray, for a O ray, and separately it is same for E ray, but for O ray and E ray along x axis or along y axis, so velocity are different. Okay. So, along the optics axis velocity or refractive index for O ray and E ray are same, but along the x axis or y axis velocity or refractive index are different for O ray and E ray. Okay. But for a only O ray along the x and y axis velocity or refractive index are same. For E ray, that is different from the O ray, the property are different from the E ray, because the velocity or refractive index for E ray are same in x axis and y axis, but that refractive index or velocity that is different from that of the O ray, right. So, in uniaxial crystal, that is calcite crystal or quartz crystal, so optics axis is very important, that is the reference axis. And what are the property of Ore and Ire in this crystal, so that we have learned. Now, we will discuss further. So, there are some devices based on this double refraction and how it is fabricated, so that we learn, and how it will be used for our experiments or for some application. So, that we will see now. Okay. So, this is a crystal. So, now we will just take one crystal. So, we are taking the calcite crystal, because calcite crystal and your quartz crystal, so it just behavior is opposite. So, next whatever we will discuss, so this we will discuss for taking the calcite crystal, because both we will not discuss, then things will be confused, but one can take example of the other crystal, other one also, but we will prefer to discuss using the calcite crystal. So, for calcite crystal, what is the property? So, for calcite crystal, this refractive index for Ore is greater than the refractive index of Ire, right. And so, this value, since along the optics axis Ore and Ire are same, their refractive index velocity are same. So, definitely whatever we are talking here, so definitely that is this value is perpendicular to the optics axis, right. So, velocity of the Ore is less than the velocity of the Ire along the perpendicular to the optics axis. Okay. Since along the optics axis, obviously both will be same, but that value will be this that is the for Ore. Whatever the value for Ore, so that will be Ire also will have the same value along the optics axis, but perpendicular direction, so they are different. Okay. So, depending on the optics axis, so we can see the behavior of Ore and Ire. So, here you see we have taken one example. So, this is the calcite crystal, this is the calcite crystal. So, this is the optics axis. So, optics axis is not a it is basically a direction, it is not a just single line. Okay. So, optics axis is along this direction. Okay. So, that is why I have done this many parallel lines, dotted lines. So, that is the direction of optics axis. It is not a single line, it is basically direction. Okay. So, this is the calcite crystal, this is the surface of this calcite crystal. So, this optics axis are like this, okay, are like this. Now, if unpolarized light, so it has two mutually perpendicular electric component, unpolarized light falls on the surface perpendicularly. Okay. So, if this is just normal glass, so what we would expect? We would expect that there will be refraction just this way, right. So, because incident angle here is 0, so refracted angle also will be 0. Yes, it happens for so we will get refraction along this direction. So, that is basically we tell that is the O ray is sigma polarized light, and this electric component will be perpendicular to the optics axis. Okay, it will be perpendicular to the optics axis because this optics axis is on the plane of incidence. Okay, optics axis is on the plane of incidence. So, O ray is sigma polarized light. So, plane of polarization. Okay. So, it will be perpendicular to this plane of incidence. So, this direction of this electric component will be this dotted one, right. So, fine. So, for ordinary glass, so it is following the basically Snell's law, right. It is following the basically Snell's law, right. So, as such here in this case, in this example, it looks like that. So, we are getting another ray, it is a refracted another ray. Okay. So, after refraction we are getting two ray, one is just following the Snell's law, this is called ordinary ray, and another is along this direction. Okay. And this ray is called the basically E ray, extraordinary ray. Okay. Now, why it is called extraordinary? It is clear that it is not following the Snell's law, right. It seems it is not following the Snell's law, but it follows. So, that we people came to know later on. So, why it is happening? No, this is happening because the refractive index are different for O ray and E ray, and it depends on the crystal. In case of normal crystal, normal glass, we cannot see this one. Also, whether you will see these two rays, separated rays, that also depends on the incidence of light, whether it is falling along the optics axis or perpendicular to the optics axis, or it is following like this. Okay. So, it depends on the optics axis of the crystal, right. So, those things were not known to earlier. So, it is a basically magic crystal. Okay. If this is the situation, somehow it is achieved. So, people for one object people used to see the two image, right. Now, if you rotate the crystal, if you rotate this crystal, just keeping this on the axis, rotation axis, if you rotate, so what happens? So, one object is constant and another object is moving on a circle about the axis of rotation. Okay. So that object which is rotating, that is basically that is formed by the E ray. So now if you consider this situation, here I am trying to show you that this refraction, double refraction, it depends on the direction of the optics axis, of course, and how crystal is cut and how the incident light is falling on it. So, it matters. So, if crystal is cut like this, calcite crystal, so this is the optics axis. So, it is perpendicular to the surface of the crystal, and now this unpolarized light is falling perpendicularly on the surface of the crystal. So, now incident angle is 0. What will happen? In this case, we will see only one refracted rays at 0 angle, angle of refraction is 0. So both cases light are falling on the surface of the crystal. So, this difference we are seeing, that is because of how the optics axis is, how the crystal is cut, and there how these optics axis are present. What is the direction of the optics axis with respect to the surface of the crystal. Okay. So, in this case velocity or refractive index are same for O ray and E ray. Okay. So, it is they are moving along the optics axis. So, they will not be separated like this. Okay. So, I told that as if this E ray does not follow the Snell's law, but that is not true. So, this happens because refractive index are different for refractive index is different for the E ray. Okay. So, that yes, I think is no, I should not tell that way. Refractive index are different, that is fine, but in this case as if here we are seeing as if it is a violating, the Snell's law is violated, right. Incident angle for both case is the for both case is the 0, but here we are seeing that E ray there is angle of refraction. So, basically for it is the definition we follow for the ordinary isotropic medium. So, in this case definition will be different. Okay. So, here definition is basically for Snell's law, if we define taking the reference of this optics axis, okay, then one can explain, could explain the that both E ray and O ray follows the Snell's law, because we write the refractive index for O ray, that is sin I by sin r. Similarly, for refractive index for E ray also we write sin I by sin r. So, extraordinary rays also follows the Snell's law, because this only we write from the Snell's law. Okay. So, both follows. So, sometimes from the angle of our conventional definition of the refractive index, okay, for isotropic medium. So, from that point of view, so as if it is violet. Okay. So, here there will not be separation of O ray and E ray, there will not be any double refraction. So, same crystal, so whether we will see the double refraction or not, so it is there, but whether it is separated or not, that depends on the direction of light and the crystal cut following the optics axis. Okay. So, how crystal was cut keeping the optics axis, in which way, in which direction. So, that is the matter for seeing the double refraction. Okay. So, in this case we will not see the double refraction. So, they will just move as usual following the ordinary glass, what happens. So, that will be followed. So, as if here you can see that optics axis, as if the whatever normal, in case of angle we consider with respect to the normal. So, as if here it is considered this with respect to the with respect to the optics axis, not with respect to the normal to the surface. Okay. In this case, if this is the optics axis, so following this optics axis, so with optics axis whatever the angle for incident angle, so for E ray, so that angle is defined not with respect to the normal, is defined with respect to the probably this optics axis. It may happen because in case of E ray, in case of E ray in this crystal, this refractive index is smaller. That means if this is the direction so whatever the normal to the surface, if you replace that one with the direction of the optics axis, so this is the direction of the optics axis, so this will be the angle, right. So this will be the angle, incident angle. Now refractive index is smaller in this crystal, refractive index is smaller, okay, than the ordinary ray. So whatever with this in this crystal, whatever this ordinary ray will make angle, extraordinary ray will make the higher angle, because refractive index for O ray is higher than the E ray. So here you will get the higher angle for E ray, right. So higher angle for E ray, if it is angle is higher, I think from here you can see if angle is higher, it is the denominator, so refractive index is lower. Okay. So Snell's law is following basically in case of E ray. So that angle, it is not with respect to the normal to the surface, that angle, incident angle and the refracted angle is defined with respect to the optics axis, okay, direction of the optics axis. So then as if this is following the Snell's law. Okay. So that's the reason we tell this in our common whatever we are habituated with the refraction in class. In that sense, it is not following the Snell's law, but it follows the normal to the surface is not considered for E ray. So optics axis is the deciding factor of the incident angle and angle of refraction. Okay. So here is fine. I discuss along the optics axis, this situation will arise, it will not be separated. And this other situation, if optics axis are this parallel to the surface of the crystal, okay. So rays are, incident rays are falling perpendicular to this surface, then in this direction perpendicular to the optics axis, okay. So here also we will not see, the separation of the O ray and E ray. We will not see the separation of the O ray and E ray, right. We will not see the probably two image. So or we can see that will depend on the situation, but this case here they are well separated, these two ray are separated. Okay. In this case both ray will follow the same path. Okay. So incident angle whatever 0, here for both rays refracted angle also 0 with respect to the normal. Okay. So but perpendicular to the optics axis, we know along the optics axis velocity or refractive index is same. Perpendicular to the optics axis, velocity for E ray and O ray are not same. So, they are different, their refractive index are different. So, in this situation what we will see, so velocity of O ray is less than the velocity of E ray in calcite crystal. In quartz crystal it will be opposite. So, this is the O ray, this is the O ray. Okay. When it will reach here, E ray will reach here. Okay. So, as if the same incident ray inside they are moving in the same direction, but there will be retardation between these O ray and E ray, whereas in this case it will not happen, they will move in with the same velocity. Here they are moving with different velocity. So, there will be retardation. Okay. So, this is it, this type of it has very important application I will discuss. So, here why I am discussing this concept is very useful for application, and that is why I emphasized on the direction of the optics axis with respect to the surface of the crystal, and also the direction of the incident light falling on the surface of the crystal, right. So, other case, if crystal is cut in such a way, this optics axis is like this. Okay. So, dotted lines, this is the optics axis. So, this is the perpendicular to this optics axis, perpendicular to the surface, to the plane of this paper. So, now in this case incident, so if incident light is falling with an angle, okay, falling with an angle. So, in this case you can see the, so they are moving basically in this plane, they will move plane of, you see, plane of incidence is this, right, plane of paper basically. So, they are moving or refracted in the plane which is perpendicular to the optics axis. So, their velocity or refractive index will be different. So, O ray and E ray will be separated. Okay. So, here as if here with this normal, okay, here we are getting O ray and E ray separated, and from this angle one can find out the refractive index for this crystal. Okay. For this crystal, calcite crystal, measuring the incident angle and the refracted angle for O ray and E ray, and calculate the, following the Snell's law, calculate the. So, Snell's law is following or not, that depends on the cut of the crystal. Okay. And in this situation it is clearly following this Snell's law, and utilizing this one can measure the refractive index of the quartz crystal or the calcite crystal in the direction to the perpendicular of the optics axis. So, this we will use in our laboratory, we will use this type of cut to demonstrate how to measure the refractive index for O ray and E ray for calcite crystal, right. So, if I continue, as I told, this concept is used for device. So, prism is a device, optical device, right. So, nickel prism. So, nickel prism, it is made of two prisms of calcite crystals. Okay. This is a device prism, it is called nickel prism. So, it is made of two prisms of calcite crystals which are cemented by Canada balsam cement. Okay. Canada balsam cement means you can attach to object, right. So, bricks basically wall, for house wall we use bricks and cement for attaching with each other. The bricks, with one bricks to the other bricks we use to attach them, we use that is called cementing. Okay, cemented. So, that is Canada balsam. So, Canada balsam, the refractive index of this Canada balsam is in middle, in intermediate, it is a basically intermediate value of refractive index for Ore and Ire. Okay. So, calcite crystal refractive index, as I mentioned, this is the 1.6584, and for Ire that is 1.4864, okay, and this is 1.55. Okay. So, it is so now this is one prism, this is one prism, and this is another prism. So, they are cemented. So, this is the Canada balsam cement. So, they are cemented like this, okay, and their optics axis are for both crystals prism, this optics axis in same direction. So, this is the single piece. If you cut a rectangular something, single piece, optics axis is like this. Now, cut along this direction, detach them and then cemented with the using the Canada balsam. Okay. So, this we tell that is a nickel prism. Okay. So, this nickel prism is used for separating the Ore and Ire, right. So, this is basically used as a polarizer. You know, polarizer is used to polarize the light, means unpolarized light is incident light is unpolarized light when it is passing through this sheet. Okay. Then we tell this is a polarized, we are getting polarized light, right. So, how it is polarized? Now it is clear. So, the sheet we use, that basically this type of, it's there are other kind of course. So, nickel prism is one type. Okay. So, this nickel prism, this is used as a polarizer. So, here what happens, refractive index for one case, it is for ordinary ray the refractive index is higher, and Canada balsam refractive index is lower. Okay. So, for ordinary ray what happens? So, from denser medium it is entering to the rarer medium, right. So, there will be, so this prism, this angle is such that when it is falling, this angle will be, when it is falling, this angle will be basically there will be internal total reflection, So, it will be reflected, whereas the other one, so it is going from, its refractive index lower, it is going from higher lower refractive index to the higher refractive index. So, both are higher. So, for extraordinary ray, so these both are basically lower refractive index 1.48 and this one is 1.5. So, from rarer medium to denser medium it is entering. So, as usual refraction will get. So, it will be refracted and it will pass like this. Okay. So, from this surface you are getting the Ore and directly you are getting the Ire. So, thus, so you design in such a way, so you will catch only this light from this surface. So, that means incident light was unpolarized light and you are getting outside the polarized light. Okay. So, it can be either O ray or it can be either E ray. So, that is basically nickel prism is used to separate this to polarize the light, okay, and the polarizer, just we tell the polarizer analyzer. So, that works based on this principle. So, next there are other prism very useful. It's called Rocon prism, Rocon prism. Okay. So, it's again calcite prism. It's made of calcite. So, it has again two part. It has two part. Okay. So, in this case this part basically here, this part, it has optics axis along this direction. So, we are taking these two part and another part is this one. So, here these two part has the different direction of optics axis. So, this is the direction of the optics axis for this part, and for other part direction of optics axis is perpendicular to the plane of the paper. So, now in this case what happens, if this is the construction of the prism, so unpolarized light is coming. So, it is from this part it is passing along the optics axis, right. It is passing along the optics axis, right. So, optics axis they will not be separated, that is what we have seen. When it is entering to the next part, so it is moving perpendicular to the optics axis. Okay. So, here E ray, so this this E ray and O ray, here we will get the E ray and O ray. Okay. So, for O ray, see its property is refractive index is basically same in all direction, velocity is same in all direction, right. But O ray that differs. So, when the same crystal, same refractive index for O ray, see it's the light is falling perpendicularly, it just go out. Okay. But E ray, it will be refracted here, because for E ray it's along the optics axis, what is the refractive index perpendicular to the optics axis, refractive index are different. So, it will be refracted along this direction. So, this it will move. Okay. So, Rocon prism is used to separate the O ray and E ray. Actually, these separation are huge. Okay. So, you can polarize the light, you can catch only one light. So, especially it is the huge separation. Okay. So, here one thing you can see, this one generally this dotted one we use for the sigma polarized light, and that is ordinary ray. So, but here it is the opposite, because in this crystal here optics axis along this direction. So, as I told, this for sigma polarized pi polarized light or for E ray. So, it is basically it is not for E ray. So, this electric component it will be parallel to the optics axis, and for O ray it is perpendicular to the optics axis. Okay. So, that is why here it looks different. So, similar case also happens if optics axis, basically optics axis are mutually perpendicular in these two half. If situation is like this, optics axis one is this and another is this, then also you can it happens that in this part it is same way here whatever we saw, because it is along the optics axis. Now, here optics axis along this direction. Now, here you can see the O ray, the polarization. Okay. This it is sigma polarized this electric component is seen now perpendicular to the plane of the paper, because optics axis is on the paper, on the plane of the paper, and this for E ray now this is on the plane of incidence, this now basically on the plane of incidence. Okay. So, O ray and E ray, here just it is opposite way. So, that is because of the direction of the optics axis. Okay. So, O ray is basically sigma polarization, and in that case electric component is perpendicular to the optics axis. E ray is pi polarization, electric component is parallel to the optics axis. So, this way also we define the sigma polarization and pi polarization. Okay. So, next another prism, see it is called Wallstone prism. Okay. In this case this two half, this half has optics axis perpendicular to the plane of paper, and other half this half optics axis is this, direction is this, and this half optics axis is perpendicular to the paper. Okay. So, here when it is entering, so it is unpolarized light, now it is going perpendicular to the optics axis, not parallel to the optics axis. Okay. So, not parallel to the optics axis. So, what will happen? Perpendicular to the optics axis, velocity of O ray, they are different. So, there will be retardation, as I mentioned. It is a parallel to the this basically surface, incident surface, right. So, they will move in same direction, but they are separated. E ray will move faster than the O ray. Now, when it is going to the other part, optics axis now perpendicular to the plane of this paper. Now, also in this case they are moving perpendicular direction to the optics axis. Okay. So, here what will happen, you know, this O ray, that is the electric component. Okay. So, now here when it will enter here, so this electric component now it will be, in this case it is perpendicular to the optics axis, but other case here it is parallel to the optics axis. So, when it is parallel to the optics axis, then it become the E ray, and other one perpendicular to the optics axis. So, that is basically O ray. Okay. So, what will happen? So, O ray in other half, O ray will be E ray, O ray will be E ray, and E ray will be O ray. So, because of that, what will happen? The refractive index for, in this part, whatever the refractive index for O ray, E ray, they are different in perpendicular direction. So, in other half it will be just exchange. Okay. Refractive index will be just exchange. Okay. And you will get this type of refraction. Okay. So, they are more well separated, they are more well separated than the Rocken prism. Rocken prism, it was going directly. So, it is so this is called Wallstone prism. So, these are very useful device for the experiment, for the application. So, that we discuss is a generally calcite crystal is used, quartz crystal can be also used. Okay. So, another important aspect, just I will tell you, that is called retarders. Okay. Retarders. So, what we have seen this, when this is the crystal, light is falling this way. Okay. Unpolarized light, and right. So, if optics axis is parallel to the surface, this is the direction. When light is moving, so E ray is moving faster than the O ray. That is what we have seen, right. So, this is used. So, when they will come out, okay. So, E ray is faster, so it will come out first, and O ray is retarded. So, both ray are moving in same direction, but O ray, E ray is moving faster than the O ray. So, their refractive index are different. Okay. So, there will be, so this retardation means there will be phase introduced when they will come out. They are falling in this incident on the same time, when same phase, okay, when coming out from this crystal. Okay. So, this there will be path difference, means phase difference between O ray and E ray, right, although they are moving the same direction. So, these plates, it is called basically retarder. Okay. So, what will be the path difference? So, if thickness is say d, okay, and refractive index for O ray and E ray is n0 ne. Okay. So, optical path for this case, one case n0 d, and for other case ned, right. So, path difference between these two rays will be this. So, this is probably n0 minus ne or ne minus n0, depending on the which one is greater. So, this. Okay. So, this basically is the path difference, between O ray and E ray. Okay. And corresponding phase difference phi will be 2 pi by lambda into this path difference delta. So, that is nothing but n0 minus ne into d. Okay. So, it depends on the, so for calcite crystal it is a n0 and ne is defined, you cannot change. Only this path difference or phase difference you can introduce, just changing the thickness. Okay. So, if thickness is such that, this phase is introduced, it is pi by 2. Okay. That means path difference is lambda by 4 or lambda by 4. Then that plate is called quarter wave plate. This is called quarter wave plate. Quarter wave plate. Okay. Okay. If thickness is such that it is introduced this phase difference pi, that means the path difference is lambda by 2. Okay. So, that plate is called half wave plate. Okay. If it is lambda, thickness is such that if it is lambda, then it is called full wave plate. And you know, it is a lambda or 2 lambda or 3 lambda, these are same. Okay. So, this is the lambda or multiple of lambda. Okay. So, this lambda by 2 or odd multiple of this lambda by 2. So, that way for quarter wave plate also. So, these plates are in laboratory for application is very important to change the polarization state. Okay. So, these two rays, when it will come out, so you will get, you can the gel, this plate one can use for linearly polarized light. Okay. If you want to get elliptically polarized light or circularly polarized light, so between two components you have to introduce the phase difference or path difference. Depending on the phase difference and path difference and the amplitude of the E ray and O ray. Okay. So, it will be decided that whether you will get elliptically polarized light or optically polarized light. So, if you want to introduce phase difference then we are using the wave plate, quarter wave plate, retarded wave plate. So, and also it can be variable wave plate. So, that is called babinet compensator. Okay. So, continuously you can vary the phase or path difference. So, that also another device that is called babinet compensator. Okay. So, I will stop here. Thank you for your attention.